Hi students, today we're going to learn about electromagnetic induction. You see, electromagnetic induction tells us what happens, when a rod moves in a magnetic field. Strange things happen. An EMF is induced in the rod. Similarly, what happens when a rod rotates in a magnetic field? We'll come to know about that in this chapter. And what happens, when any current carrying wire is placed in a time varying magnetic field? Again, something strange happens. We'll learn about all these things in the chapter Electromagnetic Induction. Understood? So let's begin. The first thing we are going to study about is magnetic flux. What is magnetic flux? Magnetic flux is simply the number of magnetic lines of force passing through a certain area. The number of field lines passing through a surface is the flux through that surface. d phi equal to b dot ds. The flux formula is that the elemental flux passing through a small elemental area ds is b dot ds. As you can see, magnetic flux is a scalar quantity because it's a dot product of two vector quantities. The unit of magnetic flux is generally taken to be Weber. All these formulae notwithstanding, you can simply understand that the net number of magnetic lines of force passing through an area is the magnetic flux. It's a symbol of the magnetism of a certain region. Now, when you have to calculate the flux phi, the general formula you can use is integral b ds cos theta. That is obvious because b dot ds is b ds cos theta. If theta and b are both constant, in that case, you can simply say flux is bs cos theta, isn't it? Theta here is the angle between the area vector and the magnetic field vector. Understood? So phi is bs cos theta. If for some reason, however, theta is not constant, or if for some reason b is not constant, in that case you will have to use the formula phi is integral b ds cos theta. As you can see in this figure, ds keeps on changing. That's because the direction of the area vector keeps on changing here. It's an undulating surface. So in all general cases, you must use the formula phi is integral b ds cos theta. Now, a fascinating law related to magnetic flux and electromagnetic induction is Faraday's law. In fact, this is the basis of electromagnetic induction. Faraday's law states that the rate of change of magnetic flux bounded by the area of a closed conducting loop is equal to the EMF induced in the loop. What this means is that whenever flux changes, an EMF is induced in an electric current loop. Understood? And the magnitude of the EMF is equal to the rate of change of magnetic flux. That's interesting, isn't it? This happens. So for example, if there's a current carrying loop and the flux through it, the magnetic flux is changing, in that case an EMF will be induced in the current carrying wire, and the EMF will be d phi by dt. That is rate of change of flux. So here we go. This is a current carrying loop. The rate of change of flux passing through this area will give us the EMF induced in the loop. So here we've learnt about a new concept that whenever you take current carrying loop and when you place it in a magnetic field, and when the flux through the loop changes, in that case an EMF is induced in the loop. This EMF is induced according to Faraday's law. Understood? Here we go. Another fascinating law that we will learn about right now is Lenz's law. You see, we've just said that EMF will be induced in the loop when magnetic flux through the loop changes. But what will be the direction of the EMF? Will it be upwards, downwards? Will it be out from the plane of the loop? The direction of the induced EMF will be such that it opposes the very cause of its production. This law was given by Lenz. Now again, we'll discuss this law in detail later, but I'll tell you the crux of the law. Let's say the magnetic field is increasing, and that's why the magnetic flux is increasing. In that case, the EMF will be induced in such a way that the current produced by the EMF will tend to decrease the net magnetic flux. Understood? So if the magnetic flux is increasing, then the EMF will be induced in such a way that the current produced by the EMF will decrease the magnetic flux. If the magnetic flux is already decreasing, then the EMF will be induced in such a way that the current produced will tend to increase the magnetic flux. Now all this might seem weird right now, but we'll learn about it soon enough. So don't worry even if you don't completely understand Lenz's law right away. First, let's tackle the big question. Now, why is an EMF induced in the first place? As I just said, let's say you have this rod here which is moving along these two rails, the green rails. Now, as you can see, the net magnetic flux passing through this loop here, the loop that I have pointed out in gray, is definitely changing, isn't it? That's because the area of that loop is changing, this loop here, isn't it? And so the magnetic flux through this loop is increasing because there's a magnetic field pointing inwards inside the screen in this region, isn't it? So there is no doubt that magnetic flux is changing in this case. Now, when this rod moves to the right with the speed v, a magnetic force acts on the electrons present in this rod downwards. That is because the magnetic force on charged particles is qv cross b, isn't it? Now B is inside the plane of the screen, V is towards the right. So when you curl your fingers from V to B, the thumb points upwards. But these are electrons. So the magnetic force on negatively charged electrons will be downwards. So the net electrons present in the wire will tend to move downwards, these green electrons. And because they move downwards, a negative potential will come in at, on the lower end of this rod, and a positive potential will come at the upper end of the rod, and therefore an EMF will be induced, isn't it? Now, since an EMF is induced, you can say that a net force EE now acts upwards on the electrons, isn't it? After all, the electric field will be directed downwards, and so because the positive terminal has been created upwards, and the negative terminal has been created at the bottom. Since the electric field is from top to bottom, the net force on the electrons is now upwards because electrons are negatively charged particles. This force will tend to balance the magnetic force downwards. The electrons will move until the electric force, because of the induced EMF, balances the magnetic force because of the motion of the rod. When these forces get balanced, EE becomes EVB, and therefore you can say that EV by L becomes EVB, where capital V here is the induced EMF, because after all the electric field is V by L, isn't it? So E, the charge on the electron, into V, the potential difference induced, divided by L, the length of the rod, equal to charge of the electron into velocity of the electrons into B, the magnetic field. On simplification, we get the value of the induced EMF as VBL. Understood? This is one formula that you have to remember. If there is any rod that's moving, in the direction shown through these rails, in that case the induced EMF is VBL. Now again, the velocity can be written as dx by dt, isn't it? If x is the distance from the origin. And BL dx by dt is what? It's BdA by dt, because L, the length of the rod, into dx is basically dA. The area moved by this rod, as it moves to the right. And therefore, the EMF comes out to be d phi by dt. We have proved Faraday's law, isn't it? This might seem difficult, but carefully try to understand what I just said. Rewind the video and you'll get it. We can even calculate the direction of this EMF. You see, Lenz's law states that, the EMF induced is such that, it tends to oppose the force that created it. So in this case, the magnetic flux is increasing as the rod moves towards the right. So, according to Lenz's law, the EMF will be in such a direction, so that the current because of the EMF produces a magnetic field which is opposite to the current magnetic field direction, isn't it? Because, if the new current induced produces an opposite direction magnetic field, then the net magnetic flux will tend to decrease, and that's what will happen according to Lenz's law. The magnetic flux is increasing and producing the EMF. So, the new current will tend to decrease the magnetic flux. Now, as you can see, the magnetic field right now is inwards into the screen. So the magnetic field, because of the induced current, should be outwards towards you, out of the screen. That can only happen if the current flows in this direction, isn't it? This direction here, like this. Because when you curl your fingers along this direction, you can see that the thumb points outwards. So the magnetic field due to the current will be outwards in this case. And therefore, as we have just discussed, the EMF will be induced in this way, with the positive terminal upwards and the negative terminal downwards, because in that case current will flow in the direction mentioned. So that is how Lenz's law will be followed. Now let's look at another interesting case where Faraday's EMF is produced. Imagine a rod like this, a metal rod that's rotating in a magnetic field. As you can see, the rod is rotating in the plane of your screen and the magnetic field is directed inwards. Now in this case, as you can see, the magnetic flux changes, isn't it? If you consider this as the starting point, in that case, clearly, as the rod rotates, the net area covered by the rod keeps on changing, isn't it? This is the net area covered by the rod. So the magnetic flux because of the rod keeps on changing as the rod rotates. In this case, also we can use the same formula. We had just discussed that when a rod moves, the EMF induced is BLV. In this case also we can use the same formula. But in this case, what is velocity? You see, in the earlier case, our rod was like this, and it was moving like this towards the right with the velocity v. In this case, this part of the rod is, moving with the velocity say v1. This part is moving with a different velocity v2, and this part is moving with a different velocity v3. If you consider any point on the rod which is at a distance x from the origin, in that case it's moving with a velocity omega x, isn't it? So there you go. The velocity of each part of the rod varies with x. So we cannot directly apply the formula, EMF equal to BLV here. In this case, we will have to calculate the EMF for every small element on this rod first, and then we can integrate the net EMF to get the final EMF induced, throughout the ends of the rod. So again, as you can see, dV, or the elemental EMF for an element that's at a distance x from the center, is b omega x dx. B L V. L for the element is dx. V, the velocity for the element, is omega x. When we simplify this expression and integrate from 0 to L, that is throughout the length of the rod, because the length of the rod is L, we get the value of the net EMF induced on the rod as p omega L square by 2. So if you have a rod rotating in a magnetic field that's facing inwards, into the screen, in that case the net EMF induced on the rod will be b omega L square by 2. This is again a very important formula for objective type questions, and you have to remember it. Again, in this case, what will be the direction of the induced EMF? The next important topic we're going to study is the charge flow due to change in flux. You see, we already know that because of change in flux, an EMF is produced, because the rate of change of flux is the same as the EMF induced in a coil, isn't it? Now, because of the EMF, a current will start flowing. There's no doubt about it. And if a current starts flowing, charge will definitely flow, isn't it? Rate of flow of charge is current. So how much charge will flow if a change in flux delta phi is carried out? That is what we are going to determine. You see, I is V by R, isn't it, where R is the resistance of the coil, and therefore the net current flowing through the loop will be 1 by R d phi by dt, isn't it, because d phi by dt is V, the EMF. Now I can be replaced by dq by dt, and so dt and dt on the left and right hand side cancels off, and you get dq equal to d phi by R. So basically on integration you get q equal to delta phi by R. This is again a very important formula. If you have to calculate the net charge that's passing through a coil because of change in magnetic flux, in that case the net charge passing will be change in magnetic flux divided by the resistance of the coil. Understood? So there you go. Remember this formula for objective type problems. Let's now calculate the work done in changing the flux by delta phi. Now we've seen this picture quite often. This picture shows you, a rod moving along two green rails, isn't it? As we already know, the magnetic flux is increasing, and therefore a current will start flowing through this loop, isn't it? Now, the current will flow in this anti-clockwise direction as shown, because as I had earlier told you, by Lenz's law, the current will flow such that the magnetic field due to the current will be opposite in direction to the original magnetic field, because the magnetic flux is increasing, so the new current will try to decrease the magnetic flux by creating an opposing magnetic field. For that to happen, the current must flow in this anti-clockwise direction. Now the point is that if you just move this rod with a velocity v and leave it, the rod will eventually come to rest. That is because a magnetic force acts on the rod because of the current induced in this loop, isn't it? As you can see, the current induced in this loop is I, and therefore the net magnetic force on a current carrying wire is IL cross B. When you curl your fingers from I to B, in that case you see that your thumb points towards the left, so the net magnetic force on the rod will be towards the left. Since the rod is moving towards the right with a velocity v, this magnetic force will try to decelerate the motion of the rod. Now the work we're talking about here is the net work that is required to be done to keep changing the flux at that same constant rate. This is the net work required to be done to keep the rod moving with the same velocity v. Now what will this work be? This work done should actually be equal to the exact amount of work that the magnetic force is doing in moving every small charge dq throughout the loop, isn't it? You see, we must keep doing work to keep producing this current I, isn't it? You see, the work done to keep the flux changing as it is the same as the work done in producing this current I again and again and again, and not allowing it to decrease. So the net work done in making the rod move constantly with a velocity v will actually be this expression, dq into v, isn't it? You see, the net work done in transporting a charge dq across a potential difference v is dq into v, isn't it? So now we want to keep the current flowing. To keep the current flowing, we have to continuously keep transporting a charge dq throughout the loop, across a potential difference v, the induced EMF. And therefore, the net work done in time dt to keep producing the same amount of the current is I dt into v, because dq is I dt, isn't it? And therefore, we can say that, the net work done in, keeping the flux increasing at the same rate is I into d phi by dt into dt, because v can be replaced by d phi by dt. The induced EMF is d phi by dt, and that gives us the net value of the work done in moving the current, in maintaining the same current constant and maintaining the same rate of increase of flux and maintaining the same velocity of this rod as I delta phi, where delta phi is the change in flux that we require. So if we want to keep the current constant, and if we want to keep the rate of change of flux constant, and if we want to keep the rod moving with a velocity v, in that case we must do work I delta phi against the magnetic force, which will try to reduce the magnetic flux and which will try to reduce the current and velocity. Understood? This is again an important formula and you have to remember it. And now that we've studied so many concepts, it's time for an IIT JEE problem. A rectangular flame ABCD made of uniform metal wire has a straight connection between E and F made of the same wire. AEFD is a square of side 1 meter and EB equal to FC equal to 0.5 meters. The entire circuit is placed in a steadily increasing uniform magnetic field directed into the plane of paper and normal to it. The rate of change of magnetic field is 1 Tesla per second. The resistance per unit length of the wire is 1 ohm per meter. Find the magnitudes and directions of the current in AE, BE and EF. Well, so let's see what's happening in this question first. We are basically given two loops, ADFE and EFCB, isn't it? The magnetic field in both the loops is facing inwards into the screen. Now it is given that the magnetic field in each loop is increasing at the rate of 1 Tesla per second. Now since the magnetic field is increasing, the magnetic flux through the loops is also changing, isn't it? The induced EMF in loop AEDF is clearly d phi by dt, isn't it? That is the area of loop AEDF into dB by dt, which is given to be 1 Tesla per second. Therefore, the net induced EMF in loop AEDF is 1 volts. Similarly, the net induced EMF in loop EBCF is 0.5 volts d phi by dt, that is the area of loop EEBCF into 1 Tesla per second. So 1 volts is induced in the loop on the left and 0.5 volts is induced on the loop on the right. We have to calculate the current through, EF, EB and AE. To calculate the current, we must first know the direction of the potential difference induced, isn't it? Now you can clearly see here, that the magnetic flux is increasing, isn't it? And it's increasing in the direction inwards into the screen. So according to Lenz's law, the EMF will be so induced that it will tend to decrease the magnetic flux, isn't it? Therefore, the current will be in such a manner, that the magnetic field, because of the current carrying wire, will actually be outwards from the screen, isn't it? Now we can see that, if we curl our fingers in the anti-clockwise direction, then clearly the magnetic field points outwards because of this current, and that magnetic field will tend to decrease the magnetic flux, isn't it? Because it's in the direction opposite to the original magnetic field. And therefore you can say that this is the direction of the current, the anti-clockwise direction. Now once we know the direction of the current, we can simply replace, this whole magnetic circuit with this electric circuit. That is because we already know that the EMF in the left loop is 1 volt, the EMF in the right loop is 0.5 volts, and the resistance of each wire is given. After all, the resistance is given as 1 ohm per meter. So according to the length, we can arrange different resistances here. So clearly, we have simplified our tough magnetism problem into a simple Kirchhoff's law problem, isn't it? And therefore, we can apply Kirchhoff's law and get the values of current in AE, BE and FE. Now, I'll not apply Kirchhoff's laws for you here. You have to use pen and paper and apply Kirchhoff's law. When you apply Kirchhoff's law, the current through EA is 7 by 22 amperes, the current through BE is 6 by 22 amperes, and the current through FE is 1 by 22 amperes. And therefore, this IIT JEE problem simply involved, using the formula d phi by dt, using Lenz's law, and then applying Kirchhoff's laws. Here's another problem that was asked in IIT JEE 1985. Space is divided by the line AD into two regions. Region 1 is field free and region 2 has a uniform magnetic field B directed into the plane of paper. ACD is a semicircular conducting loop of radius r with center at O, the plane of the loop being in the plane of the paper. The loop is now made to rotate with a constant angular velocity omega about an axis passing through O and perpendicular to the plane of the paper. The effective resistance of the loop is R. Obtain an expression for the magnitude of the induced current in the loop. Show the direction of the current when the loop is entering into region 2. Plot a graph between the induced current and the time of rotation for 2 periods of rotation. So what is happening in this question? In this question, basically the loop that you see on your screen here is being rotated in the direction shown with an angular velocity omega. The portion on the left does not have a magnetic field. The portion on the right does have a magnetic field. Now we are being asked, firstly, the magnitude of induced current in the loop. Why will current be induced in a semicircular loop if it is rotated in the manner shown? You see, as you can see, when the loop is rotated, the net magnetic flux passing through the loop keeps on increasing, isn't it? There's no doubt about it. The area of the loop which is present in the magnetic field keeps on changing as the loop keeps entering the magnetic field. Now the flux through the coil is Bs cos 0 degrees. The angle between the area vector and the magnetic field vector is the same, is 0 degrees. So the flux through the coil is Bs cos 0 degrees. Now what is B, what is S? B is definitely the magnetic field given. The area of the loop here, S here means the area of the loop that has just entered the magnetic field. The area of the loop that has entered the magnetic field at any instant is clearly theta divided by pi into pi r square by 2, isn't it? The angle entered divided by the total angle of the semicircle into area of the semicircle. And therefore, the net magnetic flux at any instant t comes out to be br square by 2 omega t, because I have replaced theta by omega t, the angular velocity into time. When you differentiate the magnetic flux, you get the value of the induced EMF. The induced EMF in the loop is d phi by dt, which is b omega r square by 2, isn't it? Now b omega r square by 2 is the induced EMF, but what is the current? Current is clearly induced EMF divided by the resistance of the loop. So the net induced current in the loop is b omega r square divided by 2r. Understood? So this is the value of the induced current in the loop. So there, we've solved the first part of the question, haven't we? It was so simple. The second part of the question asks us, to find the direction of the current when the loop is just entering the magnetic field. Now let's see what happens when the loop is entering the magnetic field. Just as the loop enters the magnetic field, the magnetic flux keeps on increasing because the area of the loop exposed to the magnetic field increases. So according to Lenz's law, the current is such that, it tends to decrease the magnetic flux. So basically, it tends to induce a magnetic field in the direction opposite to the direction, of the original magnetic field. Such a magnetic field will be created by the current in the wire only if the current is in the anti-clockwise direction. If the current is in the anti-clockwise direction and you curl your fingers in the direction of the current, you see that the magnetic field created is outwards from your screen, that is opposite to the original magnetic field. So this is the direction of the current when the loop just enters the magnetic field, isn't it? The third part of the question asks us to find out, what the graph of the current with respect to time will be. Now the magnitude of the current is clearly constant. It's b omega r square divided by 2r, and omega, b, the radius of the loop, and even the resistance are constant. The direction of the current, however, varies. You see, the direction of the current is anti-clockwise when the loop is just entering the magnetic field. But when the loop rotates and it's just about to leave the magnetic field, in that case the magnetic flux starts decreasing. When the magnetic flux was increasing, the current was induced in the anti-clockwise direction. When the magnetic flux starts decreasing, the current is induced in the clockwise direction, because again, this time when the magnetic flux is decreasing, the current is induced so that the magnetic flux increases. That is, the current induced tries to support the magnetic field that's originally there. So the new current is clockwise when the loop tries to leave the magnetic field. And therefore, when you sketch a graph, this is how your graph will be. As you can see, the current magnitude is constant, but from 0 to pi by omega, the current will have a positive value. From again pi by omega to 2 pi by omega, a negative value. Then 2 pi by omega to 3 pi by omega, a positive value, and so on. This is because the direction of the current keeps on changing, after every half rotation. That's why I've written pi by omega, because omega t is pi, for a half rotation, isn't it? So pi by omega is the half rotation time. Understood? Let's now move on to the next concept, which is Ampere's law. Ampere's law states that if a total current I crosses a closed path, in that case, the net integral, B dot dl is mu naught into I. In this case, B is the magnetic field due to all the sources at the points on the closed path. dl here represents an element on the closed path. This law seems so complicated. Where is the closed path? Where is the magnetic field? Let's clearly see, what's happening with the figure. Let's directly try to use Ampere's law by, trying to calculate the magnetic field using Ampere's law for a long wire, which is also very thick. So let us consider, a thick wire which has a radius r. Let's say a current I flows through this wire. Now, let's try to calculate the magnetic field because of this thick cylindrical wire at a distance small r from the center of the wire using Ampere's law. Now you see, Ampere's law says that integral B dot dl is mu naught into I, isn't it? Now the magnetic field, because of this current carrying wire, will clearly be tangential, to the circumference of the wire, isn't it? That's because we've already learned that for any infinite current carrying wire, the magnetic field is tangential. Now since the magnetic field is tangential, B and dl are in the same direction. So we can clearly say that B into L, or the net length of this loop, is mu naught into I. Now L here represents the entire length, which we are covering when we are trying to calculate the magnetic field. So B into 2 pi r, where r is the distance of the point where we want to calculate the magnetic field from the center of this circular wire, is mu naught into I. So B into 2 pi r is mu naught into I, and that gives us the value of the magnetic field due to a long wire, at a distance r from it, as mu naught I by 2 pi r. That's our answer. So this is how Ampere's law can be used to actually calculate the magnetic field due to a long wire. Ampere's law can also be used to calculate the magnetic field at a point inside the long wire. You see, if there's a thick long wire, then the magnetic field again, even inside the wire, will be tangential, isn't it? Now if the magnetic field is tangential, you can again apply, Ampere's law to calculate the magnetic field inside this thick wire. In this case, B into 2 pi r again will be mu naught into I enclosed. We won't consider the entire current through this thick wire because we're only taking a loop inside the wire. So we'll consider the current only up till this distance r. The current up till this distance r is r square divided by radius square into I, isn't it? After all, the area of the small loop is pi r square. The area of the entire current carrying cross section is pi into capital R square. So the value of the current enclosed by this loop that we have taken is small r square by capital R square into I. And therefore, the magnetic field, inside a long current carrying thick wire is mu naught I by 2 pi r square into small r, where small r is the distance inside the current carrying wire and capital R is the radius of the wire. Ampere's law can be similarly used to calculate the magnetic field inside a hollow pipe. Let's consider a hollow pipe like this, again, which carries a current I. Now if we take a circular loop inside this hollow pipe, in that case, that circular loop we've taken has a radius a. So B into 2 pi r is again mu naught into I enclosed. But since the pipe is hollow this time, I enclosed is 0. And so the net magnetic field inside a hollow pipe is always 0. This is an important fact often asked in competitive examinations and you have to remember it. So that was the application of Ampere's law. Let's now move on to the next concept, the concept of a time varying magnetic field. Now what we want to do in the case of a time varying magnetic field is, we want to consider a cylindrical long wire that is thick and that has a radius capital R. Now let's imagine, that along the length of this wire that is inside your screen, there's this magnetic field B. There is no current through this wire initially. Now because the magnetic field is, changing with respect to time varying magnetic field, so the net flux through this wire keeps on changing. Because of the net flux change, an EMF is induced in the wire, isn't it? Now we want to calculate this EMF first. Now clearly the flux through the wire is pi r square into B. If you consider any small area inside this wire which has a radius small r, then pi r square into B represents the flux through the wire. Now V is d phi by dt. The EMF is d phi by dt, that is pi r square dB by dt. Now we don't know whether d by dt is increasing or decreasing. So we don't know whether the flux is increasing or decreasing. Depending on whether the flux is increasing or decreasing, we can calculate the direction of the electric current and the direction of the induced EMF. That's simple enough. Now you see, what will be the direction of the electric field inside this wire because of this induced EMF? You see, if there's an induced EMF, there has to be an electric field, isn't it? Now you see, no matter what, the direction of the electric current will be tangential to the loop, isn't it? There is no doubt about it. You see, the electric current will be such according to Lenz's law that so this will either tend to increase the magnetic field or decrease the magnetic field, isn't it? Now, no matter whether the magnetic field is increased or decreased, only a tangential current can increase or decrease the magnetic field, isn't it? Because only when the current is tangential, that's when you can curl your fingers along the direction of the current and the thumb will point outwards or inwards. So definitely the current is tangential to this loop, and therefore the electric field is also tangential to the loop. Now the induced EMF is integral E dot dl, isn't it? After all, potential is always integral E dot dl, where E is the electric field. Since E and dl are in the same direction, E into 2 pi r will be V. Or you can say that the value of the net electric field inside this loop will be r by 2 into dB by dt. So we have determined this expression for the electric field inside this wire. Understood? Now what do we want to do? We want to take 2 points, present in this wire. We want to take point P and point Q, and we want to calculate the net potential difference created between these 2 points P and Q because of the time varying magnetic field. Now we know that the electric field is tangential. If the angle between the electric field and the chord PQ is theta, in that case the component of the electric field along PQ will be E cos theta. The net potential difference from P to Q will clearly be integral E cos theta dx, where x is along PQ, isn't it? That is because potential is integral electric field dot dr in the direction r. Therefore, this formula will help us calculate the value of the potential difference between P and Q. When you simplify this expression, you get Vpq equal to integral of r by 2 dB by dt into r naught by r into dx. R by 2 dB by dt is the value of the electric field. We just calculated it. Now r naught by r is cos theta. You can make that out from this figure. R naught is the distance of the chord PQ from the center of this entire wire, isn't it? So clearly this is the value of Vpq. When you further simplify this expression, you get the value of the net potential difference between 2 points P and Q on any wire, in which there's a time varying magnetic field as r naught square root of r square minus r naught square into dB by dt. So this is again an expression you have to remember for competitive examinations. If you have a long wire, which is also thick, and if there's a magnetic field acting inwards into the wire, in that case, the net potential difference between any 2 points on the circumference of the wire is r naught square root of r square minus r naught square into dB by dt. R naught is the distance of the chord PQ from the center of the wire. Now that we've studied so much, about magnetic flux and how it changes, let's learn another interesting concept, the concept of self-induction. The phenomenon of generation of induced EMF in a coil due to the change in flux bounded by the coil because of its own magnetic field is called self-induction. Now you see, self-induction is very interesting. Let's say you have a coil and this coil carries current. In that case, there will be some magnetic field because of this coil, isn't it? After all, a current carrying coil generates a magnetic field. Now if this magnetic field actually changes, or the net magnetic flux through this coil changes, in that case an EMF will be induced in this coil because of Faraday's law. So the fascinating fact is that because of the current in the coil itself, the magnetic field is being produced, and because of the change in the magnetic field, a new current is being produced, an induction current. So this phenomenon of one current producing a magnetic field and the changing magnetic field again producing an induced EMF and induced current is called self-induction. It appears complicated, but it is actually quite simple. Now let us try to calculate the induced EMF because of the current in the coil. You see, let's take this solenoid, a solenoid consisting of different coils. Now the magnetic field because of the solenoid will be towards the right, if the current is in the direction shown. That's because when you curl your fingers in the direction of the current, the magnetic field is to the right. Now, let's assume that the magnetic flux through this coil is increasing, because let's say the magnetic field is increasing. In that case, according to Lenz's law, the current will be induced in such a way that it should create an opposing magnetic field. An opposing magnetic field will be created by a current in the opposite direction, isn't it? And therefore, you can see that the induced current will be such that it creates an opposing magnetic field. If n phi represents the net flux through this solenoid, in that case you can clearly say that Na into mu naught Ni by L is the net flux through this solenoid. N is the number of turns through the solenoid, isn't it? And mu naught Ni by L is clearly the magnetic field because of a solenoid. We had already studied that earlier. When you simplify this expression, you get mu naught N square A by L into I. Mu naught N square AI by L basically tells us the value of the net flux passing through the solenoid. Now this term mu naught N square A by L is often referred to as the self-inductance L. So you should remember that the self-inductance of a solenoid is mu naught N square A by L. Now what will be the induced EMF? Clearly N phi is Li. The net flux is Li. So the induced EMF in the solenoid will be dN phi by dt, which is LdI by dt. And this is the expression that you must remember. If any substance has a self-inductance L, in that case the net EMF induced on it, because of the own current that's flowing inside it, is LdI by dt. So if this is a varying EMF here, then current will be induced, and basically you will be able to replace this entire solenoid by a reverse battery of magnitude LdI by dt. You see, basically an EMF LdI by dt has been induced, so that current carrying wire has actually gotten converted into a battery with whose EMF is creating current in the direction opposite to the direction of the battery. Again, that is also obvious, because according to Lenz's law, the EMF opposes the force that created it. So this EMF tends to oppose the current which caused its production, and therefore LdI by dt can replace any solenoid that's connected to a varying EMF. In fact, any curved wire, something like this, is called an inductor. You see, any inductor can always be replaced by a battery LdI by dt, such that the battery opposes the original current in the circuit. Understood? This is very, very important. Inductor is basically any substance which has a self-inductance or which has a tendency to get an EMF induced on itself. We can also calculate the energy stored in an inductor very easily. You see, the energy stored in an inductor is basically the work done in carrying the charge from one end of the inductor to the other end of the inductor. Now let's carry a charge dq from one end of the inductor to the other end. Then the energy stored will be integral dq into V, where V is the potential difference across the inductor. And therefore, the net energy stored in the inductor will be integral dq into LdI by dt, because the EMF or the potential difference across the inductor is LdI by dt. So the net energy stored in the inductor will be integral I dt into LdI by dt, or it will be half Li square. So you must remember that the net energy stored in any substance which has a self-inductance L is half Li square. This is very important for competitive exams. Another interesting concept that's only slightly different from self-induction is mutual induction. The phenomenon of generation of induced EMF in a coil due to the change in flux bounded by the coil because of the magnetic field produced by the current flowing in another coil inside it is called mutual induction. Now this statement might sound quite tough, but it's actually quite easy. You see, let's say we have a coil like this, and let's say we have another coil that surrounds this coil. Now the initial black coil actually it's connected to a battery, but this green coil is not connected to any battery. Now if the current through this black coil varies, then the flux through the black coil will vary, because the magnetic field of the black coil will vary. Because of the variation, an EMF will be induced. The magnetic flux through the green coil will also vary, isn't it? Because after all a portion of the green coil is enclosed by the black coil, isn't it? And so the EMF induced in the green coil because of the black coil's magnetic field is called mutual induction. Understood? So basically, earlier self-induction, what it involved was that the magnetic field was changing through a coil, and so because of the changing magnetic field, the flux through the coil was changing and an EMF was induced in the coil. Now, we have a coil covering the original coil, and because of the change in flux of the original coil, the net flux through the covering coil is changing and an EMF is induced in the covering coil. This phenomenon is called mutual induction. Interesting, isn't it? If the inner coil has, N1 turns, and if the outer coil has N2 turns, we can actually calculate the net change in flux of the outer coil. The net flux through the outer coil is clearly N2 into phi 2, if N2 is the number of turns in the outer coil. Now again, phi, the flux, is basically mu naught N1 I1 by L1, that is the magnetic field because of the inner coil into N2A1. So basically, N2A1 represents the area of the outer coil, loops, and the number of turns in the outer coil loops. But the magnetic field that we have considered is the magnetic field of the inner coil. That is mu naught N1 I1 by L1. The field of the inner coil is that expression. On simplification, we get the net flux through the outer coil as mu naught N1 N2 A1 I1 by L1. This term here, mu naught N1 N2 A1 by L1, is called the mutual induction of a system of coils. Understood? So this is again a very, very important expression, and you have to remember it. The formula for mutual induction. The next concept that we are going to study is the RL circuit. An RL circuit is basically a circuit consisting of a resistor and an inductor. An inductor, I must remind you, is any substance that can have an EMF induced on it because of the current passing through it. Now, what will be the current passing through an RL circuit? Clearly, if we apply Kirchhoff's law, we will see that L di by dt plus IR minus E is 0. Note that I have written different signs for the EMF induced in the inductor, which is L di by dt, and E, the EMF of the original battery, because the EMF in the inductor will always be in the direction opposite to the EMF of the battery. Now if we integrate this expression after taking sides, we get integral di by E minus IR equal to dt by L, and on further simplification we get minus 1 by R ln of E minus IR equal to t by L plus constant. On final simplification of this simple Kirchhoff's law application, we get the value of the net current flowing through the RL circuit as this expression. The net current flowing through the RL circuit is E by R into 1 minus E raised to minus t by L by R. This is a very, very important expression, and you have to remember it. This expression tells you the value of the net current flowing through an RL circuit. You can depict this current on a graph. As you can see, the current keeps on increasing with time, but the rate of increase of the current keeps on decreasing with time, isn't it? Now if the current is this expression, we can also determine the induced EMF in the inductor. The induced EMF is L di by dt, so we can differentiate this current and multiply that value by L. When we do that, we get the value of the net induced EMF as this expression. Understood? There we go. This is the variation of the induced EMF with time. As you can see, as the time increases, the induced EMF goes on decreasing. At time that t tending to infinity, there's hardly any EMF induced. Understood? Let's now solve a problem asked in IIT JEE 1996 related to RL circuits. A solenoid has an inductance of 10 Henry and a resistance of 2 ohms. It is connected to a 10 volts battery. How long will it take for the magnetic energy to reach 1/4 of its maximum value? Now at first glance, this problem is very tough, but let's draw a diagram first. This question basically has a battery of 10 volts, a resistor of 2 ohms, and an inductor of inductance 10 Henry. By the way, I forgot to mention earlier that Henry is the unit of inductance. So that's the SI unit of inductance, and you'll be encountering this unit often. Now in this IIT JEE problem, we have to first calculate the time in which the energy of the circuit will be 1/4 of the maximum energy. Now we know that the energy is half Li square, but we have to find out U. Now we also know that U is 1 by 4 of U max when I is half of I max, isn't it? That's because U is half Li square, so magnetic energy is proportional to I square. So magnetic energy will be 1/4 when current will be half of its maximum value. Now the expression for current is this expression, I equal to I naught into 1 minus e raised to minus t by L by R. E by R is the maximum current through the circuit, isn't it? Now since I equal to I naught into 1 minus e raised to minus t by L by R, we can substitute the value of L here as 10 Henry, R here as 2 ohms, and we can write I as I naught by 2, that is half of the maximum current. When we do that, we get the net value of time at which the current is half of its maximum value as 3.465 seconds. This is also the time at which the magnetic energy is 1/4 of its maximum value. So there you go. Solving this IITJ problem was quite simple.